Alright everyone, hello and welcome to another online lecture. This is section 12.1 from the Briggs textbook, and today we're studying parametric equations. So this chapter, chapter 12, is all about parametric equations and polar equations. Those are terms that perhaps you're familiar with from other classes. Maybe you've learned about them already in physics. But we're going to study them pretty in depth here in calculus. And also, Chapter 12 is very different than everything else that we've learned this entire semester. So if you found yourself lost and confused about all of the previous material, at least this chapter is like a fresh start. You do not really need a ton of the information that we've learned so far in order to do the content in this chapter. It is very different. Alright, so let's go ahead and jump into it. The first thing, let me give you guys a little bit of an overview. This graph that I have here at the top, this little butterfly looking thing, using the methods that we've learned in like high school algebra, it would actually be very difficult to graph this curve. Today what we're going to do is we're going to introduce a system that can graph a curve like this. The equations that we use to create such a curve are called parametric equations. And we're going to note that this curve is not a function in particular, so we can't say that that curve is a function because it fails the vertical line test. Remember that in order to be a function, you should be able to draw a vertical line, and at any point, your vertical line will pass through the curve exactly once. Since that is not true for this curve, it is not a function. Alright, so the essential idea behind parametric equations is that the x-coordinate and the y-coordinates are now functions of a time variable t. This variable t is called a parameter. As t changes, the curve's x and y coordinates will change, and we can eventually sketch out the curve. So more systematically, what I mean is that in general, we have equations that look like x is a function of t, and y is another function of t. And throughout the course of this section, we are going to let f of t be the function associated with x, and g of t be the function associated with y. And f and g are given functions, and the variable t varies over some specified interval. So maybe t varies from 0 to 1, or 0 to infinity, or negative infinity to positive infinity, whatever. The curve that is sketched out by these equations over that interval t is called a parametric curve. So generally, we have the independent variable x and the dependent variable y, and it's just a standard two-variable description of our particular curve. Here, however, we have the independent variable t and the dependent variables x and y, which will tell you the x and y coordinates for your function. And this will have some advantages that we will see soon. So let's go ahead and look at an example of such a function. Consider the function that is defined by these parametric equations. We have x equals 2t, and y equals 1/2 t squared minus 4 from 0 to 8. So t varies from 0 to 8. One way that you can graph this curve is to draw out a chart. So you can plot t, x, and y for a bunch of different values, and then figure out what the points on your graph are going to be. So for example, if we look at t equals 0, the x-coordinate, of course, will be 0, because if you plug in t equals 0 right here, you would get 0. And if you plug in t equals 0 right there, then you would just get negative 4. And so the y-coordinate is negative 4. And so one coordinate on our curve is 0, 4. If you do this for a bunch of different values for t, you can eventually connect the dots and sketch out a curve. And so for this one, we did this for all the integers, 0 through 8, and we were able to sketch out this curve. So hopefully that makes sense. The basic idea is that t is the independent variable and x and y are the dependent variables. All right, so a quick discussion, a couple things that we want to make note of here. In this preceding example, the first thing that we want to note is that the curve has arrows on it. Let's take a look again at this curve. You'll notice that there are these blue arrows throughout the curve. The basic idea is that those arrows indicate the direction that t was increasing. So t started at 0, and then that was this point, and t ended at 8, and that corresponded to this point. So as t increased from 0 to 8, the arrows indicate the direction of increase. This can have particular advantages for us, because if we seek to monitor the motion of an object, then we may wish to know exactly the path that was taken. And so the arrows, a parametric description of our curve, could do that better than just writing it in the standard XY sense. We also call the direction that t was increasing the positive orientation of the curve. And as you might guess, if you were to consider the opposite direction of that, it would be the negative orientation. The second thing is that sometimes it is possible to write this curve using standard xy coordinates, so to write it in a Cartesian form. Doing this, this process is ultimately called eliminating the parameter. Alright, so for this previous example, the basic idea is that we want to try and get rid of t. Right, so we had the functions, let's look again, x equals 2t and y equals 1/2 t squared minus 4. So let's write those down again. X equals 2t and y equals 1/2 t squared minus 4. If we want to eliminate the parameter, one general strategy is to rewrite one of these equations and solve it for t. So let's solve this first equation for t. We can write that t is equal to x over 2. And what we will do now is we are going to throw this x over 2 into this t here. And so that's going to give us y equals 1/2 times x over 2 quantity squared minus 4. And if we simplify this a little bit, we get y equals x squared over 8 minus 4. All right. The next thing to consider, so that was eliminating the parameter. We got rid of our t variable and we wrote it in terms of Cartesian coordinates. We now just have y's and x's, which is what we desired. So the next thing we want to consider is the parametric equations for lines. So lines have a very special parametric form. In particular, we're going to consider the parametric equations x equals x naught plus at and y equals y naught plus bt, where t varies from negative infinity to positive infinity, and x naught, y naught, a, and b are all constants. So first, let's just consider what happens when we eliminate the parameter. So the variable here is t, and we want to solve one of these two equations for that. So let's solve the first one for t. If we do that, we're going to get t equals x minus x naught all divided by a. And we are going to throw this and insert it right there. And so that will give us that y is equal to y naught plus b times x minus x naught all over a. And if we write this a little cleaner, we get that y minus y naught equals b over a times x minus x naught. And does this look familiar? Hopefully it looks at least a little bit familiar. This is exactly point slope form for a line, where our slope is b over a and the coordinate, the point that it goes through, is x naught, y naught. Alright, and so the basic idea here is that if you want to write a line in parametric equations, one way to do that is using these two parametric equations. It is certainly not the only way, but it is a way to do it. Alright, so the summary down here kind of gives the idea. The only caveat they say here is that if a is equal to 0 and b is not equal to 0, then the line is actually vertical. So if you were to describe x equals 5 and y equals anything, let's say 2 plus 3t, then that would be a vertical line. Alright, so let's do an example. Consider the parametric equations given here. These are certainly in the form that we just discussed, x naught plus at, and then y equals y naught plus bt. T varies from negative infinity to positive infinity. We're going to find the slope-intercept form of this line. So not the point slope form, like we discussed on the last slide, but the slope-intercept form. Alright, so we have, let's first of all just start with our point slope form. We know that y minus y naught equals b over a times x minus x naught. So in this case, it's helpful to identify what all of our pieces are. Negative 2 is our x naught, 3 is a, 4 is y naught, and negative 6 is our b. So let's just replace all of that in our equation. We have y minus 4 equals negative 6 over 3 times x minus x naught, so that's really x minus negative 2, or x plus 2. If we simplify this a little bit, we get y minus 4 equals negative 2 times x plus 2. Y minus 4 equals negative 2x minus 4. Add 4 to both sides, and you get y equals negative 2x. And that's what we wanted. We wanted something that was in slope-intercept form, and this is precisely what we got. We could go one step further and describe what the domain for this function is. We know that x is going to vary from negative infinity to positive infinity. And also, for that matter, y will vary from negative infinity to positive infinity, because this is just a line that looks like this. Alright? And let's think for a second whether this function, let me actually make this picture look a little bit nicer. Let's think for a second. This graph, which direction should the arrows be pointing? Should they be pointing downward or upward, to the right or to the left? if t is increasing from negative infinity to positive infinity, then let's just consider what happens at a negative value for t and a positive value for t. At a negative value, then we would get something. I want to explain this in a slightly different way. Let's look at both the x and y functions. The x function is an increasing function of t. If you increase t, you will increase x, right? Because that 3 is positive. So it is an increasing function of t. So as you increase t, x should increase. That indicates that your arrow should go like this, because you are increasing in the x direction. Also, as you increase t in this y function, you will actually decrease y. So y is a decreasing function of t. And so as you increase t, y will decrease. So once again, that gives you the indication that the arrows should point downwards. All right, so both of those should make sense. All right, let's do another example with lines. We're going to find two pairs of parametric equations with opposite orientations for the line with slope 1/3 that passes through the point 2, 1. All right, so if the slope is 1/3, that's m, but m is really b over a, and the point 2, 1 is really the point x naught, y naught. And so what we're going to do is there's an infinite number of ways that we can represent this line. Let's just do a few. So we can write that x is equal to, so it's in general x naught plus at, and y equals y naught plus bt. So this is the general way that we write it. X naught in this case is 2. A, let's just go ahead and say that it's 3, right? So we can say that a is 3, because if m is equal to b over a, let's just say that a is the denominator. A is 3. Then we'll say that b is 1. So y is equal to 1. Whoa. Y is equal to 1 plus t. And so in this case, we said that b over a was equal to 3 over 1. Alright, so if this were the case, the idea is that as t increases, x increases, and so this will be an increasing function of t. Similarly, y is an increasing function of t, so this point, which we will draw over here, or this function, which goes through the point 2, 1, let's say it's right there, and it has a slope of 1/3, so perhaps it's a really shallow function, looks something like that maybe. Then, since this is increasing in both x and y, we can write that the arrows go like this. Alright, let's try another example. Now we want it to point in the opposite direction. So basically what we want is we want it to be a decreasing function of x and a decreasing function of y. And so we can just simply replace x equals 2 minus 3t and y equals 1 minus t. Then our slope, b over a, is equal to just negative 3 over negative 1. I made a mistake earlier. This should be 1/3, and then this should be -1 over -3. Yeah, better. Which, of course, is just 1/3 as we desired. All right, and so then this function, once again, here's our point, 2, 1. Our graph goes through this point, perhaps like that. And since it's a decreasing function of x and a decreasing function of y, then we can draw the arrows in the opposite direction. It is both going downward and leftward. And so those are two different ways to represent the same line with opposite orientations. There are infinitely many other ways that we could represent this line. For example, let me just give you one. You could, instead of saying x equals 2 plus 3t, you could also say x equals 2 plus 6t, and y equals 1 plus 2t. Then you would get b over a equals 2 over 6, which again is 1/3, so it's the same line, and it would actually be the same orientation as this guy. So infinitely many ways to express the same line, and you can express it with different orientations if you want to. Okay, let's consider now bridging away from linearity and going into circles. So in xy coordinates, the Cartesian equation for a circle centered at the origin with a radius of r is x squared plus y squared equals r squared. Hopefully you're familiar with that. So for example, if we wanted to write the equation for a circle of radius 2 centered at the origin, the Cartesian equation would just be x squared plus y squared equals 2 squared, which is 4. All right, and what we're going to do is we're going to show that the parametric equations given by x equals 4 cosine t and y equals 4 sine of t, under these bounds, 0 to 2 pi, represent a circle of radius 4 centered at the origin in 4 different ways. So the first method that we want to go through is to create a table. So basically, let's just plot a few values for t and consider what happens to x and y. So at t equals 0, then x would ultimately be 4 times 1, which is 4, and y would be 4 times 0, which is 0. At pi over 2, it's the opposite, 0 and 4. At pi, it's negative 4, 0. At 3 pi over 2, it's 0, 4. Or 0, negative 4, sorry. And at 2 pi, it will be 4, 0 again. And so we can plot all of these points. Let's go ahead and label our graph a little bit, perhaps. So let's say that right there, right there, right there, and right there are the values for negative 4 and positive 4. So here's 4, 4, negative 4, negative 4. And let's see how good my drawing skills are. This is not quite a great drawing, so let me make it a little bit more accurate. I think so. And it creates a circle, so not bad. So basically all we really did was we noticed that there were points at 4, 0, which was right here, 0, 4, negative 4, 0, and 0, negative 4, which are those 4 points. What we should have probably done is considered a lot more points, because we don't know if the graph really is a circle, or perhaps it's a diamond. It looks something like this maybe. Or perhaps it looks more like a star. just based off of those 4 dots, it's not quite apparent. You would really need some more information. So what we really should have done is we should have considered points like pi over 4, pi over 8, 3 pi over 4, etc. But I assure you that when you do consider more points, you would get a better approximation for your curve. So let me clean this up a little bit. So that's method 1. It's just creating a t-chart. Create a table, and then plot a bunch of points, connect the dots. That can work some of the time, but if you don't want to have to compute a ton of values, one thing that you could instead try to do is use graphing software. For example, the website Desmos works pretty well, and so it actually has a component to do parametric graphing. I'm not quite going to show that here, but I would recommend that you definitely check this out on your own time if you're ever curious about what a graph looks like. And so, yeah, it's a great resource. The third method, which involves a little bit of math, is eliminating the parameter. So if we want to eliminate a parameter, then the thing that we did in the previous examples, where we solved one variable for t, and then plugged it into the other one, it's not going to be quite so easy to do here, because we have x equals 4 cosine t and y equals 4 sine t. And that's going to cause us a little bit of an issue. So, to eliminate the parameter, there's 2 different ways that I'm going to show you how to do that. The first way that I would like to demonstrate is with the following. So let's rewrite our functions. X equals 4 cosine t. Y equals 4 sine t. What I'm going to do first is I'm going to square both of these. So we're going to write that x squared is equal to 16 cosine squared of t. And likewise, I'm going to square this function over here. So we have y squared equals 16 sine squared of t. Now what I'm going to do is I'm going to add these 2 equations together. And that concept I think we've done a little bit before in this class. But the basic idea is we add the left-hand sides and the right-hand sides together. So if I say that x squared, if I want to consider x squared plus y squared, then that better be equal to the sum of the right-hand sides. Alright, so sum of the left-hand sides is equal to the sum of the right-hand sides. And doing that, we get that x squared plus y squared is equal to 16 cosine squared of t plus 16 sine squared of t. Now perhaps you see where I'm going. The next strategy, the next step is to factor out that 16, of course. Oops. And sine squared of t plus cosine squared of t is just 1. So this is just equal to 16. And we get the equation that we wanted all along, which was that x squared plus y squared is equal to 16. And we have eliminated the parameter. There's no longer a t inside this equation. So I guess the idea here is to notice that when your function includes sine and cosine, perhaps you could consider isolating. Let me not say that. You could consider getting this to a form where you get sine squared of t plus cosine squared of t, and then things should simplify. Let's try the second method of eliminating the parameter down below. In this case, what I want to do is I actually want to approach this slightly differently. Rather than figuring out a way to get sine squared plus cosine squared, let me actually do this. I'm going to write that x over 4 is equal to cosine of t. Certainly that's true if I just take this equation and divide both sides by 4. Then, this actually represents a right triangle. Let me try again. Better. Alright, and the right triangle that is represented here has this angle of t. And since we know that cosine of t is equal to x over 4, and cosine is adjacent over hypotenuse, this essentially means that x over 4 are in these spots. And then we can fill in this other leg. We know that this is going to be 16 minus x squared. Alright, so we had the y equation, y equals 4 sine of t, and now suddenly we know how to replace sine of t using this triangle. In particular, the sine of this angle t is the opposite over the hypotenuse. And so we may write that y is equal to 4 times root 16 minus x squared all over 4. Of course, the 4's will cancel out. So we're left with y equals root 16 minus x squared. If we now square both sides, then we will get y squared is equal to 16 minus x squared. And once again, if you add x squared to both sides, you should conclude that x squared plus y squared equals 16, indicating that we have correctly identified this as a circle. So we eliminated the parameter in 2 different ways on this problem. The first way was we just squared both sides, added them together. Notice that sine squared plus cosine squared is 1, and factor out that 16. Second way, we used a triangle and plugged this triangle's information in for sine of t, and eventually we're able to conclude that x squared plus y squared equals 16. Alright, so now let's do one that's a little bit trickier. Let's consider eliminating the parameter to find the Cartesian equation for this function. X equals 5 sine of t, and y equals 2 cosine squared of t, where t varies from 0 to 2 pi. Alright, so this one, we can't quite do it as simply as this first elimination of the parameter, because we can't just simply square both sides and then add them together. And we also can't quite just square this one and add it to this guy, because then we would get 25 sine squared of t, and you can't just add that to 2 cosine squared of t, because you can't factor out anything to get sine squared of t plus cosine squared of t. So this method doesn't work. So there are still 2 ways to do this along the same line of thinking. Let me use the triangle method for this guy. So for the triangle, once again, we are going to isolate our sine of t. I also want to make sure that I work with this function and not this function. The reason for it is because this one has a cosine squared of t, and that's just a little bit trickier to deal with. So I'm going to start with the sine of t function. So we may write that x over 5 is equal to sine of t. This expresses a right triangle. Yikes. Let's try again. Better. Here's the angle t. Sine is opposite over hypotenuse, so here's x, here's 5, and then this leg must be 25 minus x squared. Alright, so then we know that cosine of t is just adjacent over hypotenuse. So cosine squared of t must be adjacent over hypotenuse, that whole thing squared. So let's write that down. We now know that y is equal to 2 times root 25 minus x squared all over 5, this entire thing squared. Alright, so let's simplify this a little bit. We're going to end up with 2 times 25 minus x squared all over 25. Alright, well, we can split up that fraction. We would really just get 1 minus x squared over 25. And if we distribute the 2, we get 2 minus 2 25ths x squared. Alright, and we have officially eliminated the parameter. There's no longer a t in here. And yeah, that's pretty nice. So let's once again read the instructions, make sure that we've done everything. We need to eliminate the parameter to find a Cartesian equation. Alright, done. But we also need to include bounds for both x and y, and we need to describe the resulting curve, or draw it. So, to describe this curve, it is sufficient to say that this is a downward-facing parabola with a vertex at 0, 2, and that's probably sufficient. So this, let me box my answer. Parabola with vertex at 0, 2. Alright. The reason I know that there's a vertex at 0, 2 is because this is basically just your normal parabola, just shifted up 2 units, and it's slightly wider. Okay. So we also want to include bounds for both x and y. So the way that we do that is we should look at our function x equals 5 sine of t and y equals 2 cosine squared of t and ask ourselves, what are the highest and smallest numbers that x can take on between 0 and 2 pi? So this value for x will range between -5 and +5 within these bounds, right? Because sine varies between -1 and +1. And so we may write that -5 is less than or equal to x, which is less than or equal to +5. So those are the bounds for x. The bounds for y, all right, so let's think about this. Cosine of t, just cosine of t, not cosine squared. Cosine of t ranges between -1 and +1. Cosine squared of t ranges between 0 and 1. So that means that 2 cosine squared of t must range between 0 and 2. So we write that 0 is less than or equal to y, which is less than or equal to 2. Alright, and these values will certainly occur within my interval here. So if this interval were shortened, let's say instead of 0 to 2 pi, let's say it was 0 to pi over 4, then perhaps these intervals would change, because perhaps I don't get my maximum value for x or y within that interval. So it's important to check what your interval for t is here to consider what happens to x and y. But because t ranges from 0 to 2 pi, every value for sine will be achieved and every value for cosine will be achieved. All right, let's continue. Next, we're going to consider the example where we have to parameterize the equations of curves. So in the previous examples, we have eliminated the parameter. So we started with parametric equations and we wrote it as a Cartesian equation. In these next two examples, we are going to start with a Cartesian equation and we are going to write it as a parametric equation. So the first one that we have is y equals 9 minus x squared, and x ranges between -1 and 3. All right, so the thing about these particular problems is that you will notice that this is a function, right? Y is equal to 9 minus x squared. That is a function because it passes the vertical line test. So this is just a downward facing parabola, and that certainly passes the vertical line test. Since it is a function of the variable x, we may say that x equals t and y equals 9 minus t squared. And it's easy to see that you could just plug in x right here and you would get back your original function, y equals 9 minus x squared. We should include bounds for t. So since t varies from -1 to 3, since x varies from -1 to 3, t must vary between -1 and 3. And one of the things that's interesting about parametric equations is that there is not a unique representation for any curve using parametric equations. In fact, for any curve that you can draw, this parabola for example, there are infinitely many ways to express that parabola using parametric equations. One way to do it is like this. This is arguably the easiest way. I could instead choose to parameterize it in this way. I could say x equals 2t and y equals 9 minus 2t squared. And in this case, -1 is less than or equal to 2t, which is less than 3, which is the same thing as saying that -1/2 is less than or equal to t, which is less than or equal to 3/2. And this is also an equivalent parameterization. And you could imagine changing x to be anything you possibly want, and then changing this t to be that same thing, and it would work out. And we actually do this down here at the bottom. Here we say, you could let x equal 1 minus t, and then you just replace the t with 1 minus t quantity squared. And then your bounds are -2 to 2. The advantage of changing it sometimes might be that you get better bounds for t. So in this first example, you have t ranges from -1 to 3. Let's say for whatever reason you wanted t to range from 0 to 1. Those always look nice when t ranges from 0 to 1. Then you might have to find a particular x to throw in there, and then t would have to be the same thing. I think you could just do x equals 1 minus t all over 2, and then this thing all over 2. No, I think you would need this whole thing times 2, this whole thing times 2. Yeah, and then, I don't know, it's something like that. And then perhaps you would get better bounds. Anyway, the idea is that it will change your bounds for t, and perhaps it'll make it look better. All right, there's infinitely many ways to express any curve using parametric equations. All right, so we can also use this to find the representation for the curve representing the right half of a circle of radius 3 generated clockwise. All right, so let's give this a shot. So first of all, let's draw what we are looking for. All right, let's see how well I can draw this. We want a circle of radius 3. So here's 3, here's -3, and that's 3 as well. Okay. And we want this thing to be generated clockwise. When it says generated, that means that the arrows point in a clockwise manner. If we go back to our original circle, I should have specified this earlier. This is actually generated counterclockwise. And so what you'll notice is that the first point that we had at 0, at t equals 0, occurred right here. The second point occurred at t equals pi over 2, right up here. This was t equals pi. And then this was t equals 3 pi over 2. And so the arrows actually are generated in a counterclockwise manner. And so normally our circle is counterclockwise. In this example, we want a clockwise circle. Okay? So, once again, there are infinitely many ways to do this. Let me just kind of walk you through what my thought process would be doing something like this. We certainly know that the first point we want to have is up here at 0, 3. So first point is at 0, 3. Halfway along our interval, we want the point 3, 0. And at the end, we want the point 0, -3. All right, so how do we achieve that? Let's start with what we had in the first circle example. So we had x equals 3 cosine t and y equals 3 sine t. And let's just change our bounds for t and see what happens. So let's say, if we do, our first guess might be, let's try 0 to pi and see what happens. All right, well, if we do 0 to pi, then the first point that we would get is x equals 3 and y equals 0. So that would be this point. And then the last point we would get would occur at pi, which would give us x equals -3, y equals 0. So we would actually end up tracing out this curve. All right, so perhaps that's not quite the right bounds for t to use. Let's try a different one. Let's say, I don't know. Let's go pi over 2 to 3 pi over 2. All right, well then the first point that we would get would be at x equals 0 and y equals 3. So 0, 3, that's the good first start. Our halfway point would occur at t equals pi. So we would get x equals 3 and y equals 0. Sorry. Yeah, at t equals pi, we would get y equals 0. Yeah, that works. And so we would start to trace out this point. And then at 3 pi over 2, we would get 3. And then if we plug in pi over 2, we would get cosine of pi over 2 is 0. And 3 times sine of pi over 2, 3 times sine of 3 pi over 2 should be -3. And so, yes, we do indeed end up down here. And so it looks like this parameterization, these bounds for t will work. And so if we just start off with our original equations and throw these in, that will be sufficient. Okay. This is actually not the one that I was intending on showing you guys. This happened to just be a random guess that worked out. But there are infinitely many ways to do this. The one that I was intending on showing you was actually x equals 3 cosine t, y equals -3 sine of t. Notice we had to change this and make it negative, and then our bounds would be -pi/2 less than or equal to t, which is less than or equal to pi/2. And this kind of looks a little bit more attractive, perhaps, because we have symmetric bounds around 0. There's also another way we could have done this. We could have just simply said x equals 3 sine of t, and y equals 3 cosine of t, and t ranges from 0 to pi. All of these parameterizations will work. Whichever one you find the most attractive is whatever you should go with. Perhaps on an exam, we would give you a multiple choice and say which one of these represents the parametric equation of this graph, and then we would give you maybe this guy and then 3 false answers. And so it's important to note that there are infinitely many ways to express the parametric equation of this graph, but it's good to be able to identify more than one. All right, so all we've done so far is talk about graphing. So the next thing that we will do is we will talk about the calculus of parametric curves. And to do that, I think I actually want to pause and start that in a new video. So let me go ahead and pause here, and I will see you in the next video.